we will see that what is meant by thrashing. See, let us see how our process will look like. You know that, right? Our process will have code segment, data segment, stack segment, and heap segment. See, this thing we have already seen in operating systems part 1 course, right? But anyway, it is not that important. Actually, it is very important in computer architecture and organization. It is not that important here, but I will give you a rough idea. See, this is where our code will be present. Our process will have a code, right? Program. That program will be present over here. The data means the variables which we are having in our program will be maintained in the data segment. Fine. These two, it is not important right now. Okay. Now let us assume this is how our process P1 is looking like, right? Now let us assume our process P1 is having an instruction named as add A, B, C. What it means is A and B, the value of A and B will be added and the result will be stored in variable C. Okay, that is what we mean by add A comma B comma C, which means A and B will be added and the result will be stored in C. Let us assume in the data segment, see the data segment we will have the values of variables, right? We are having values of variable. Sorry, let us assume add A, B, C means we are going to add B and C and then we are going to store the result in A, right? See, B and C are two variables and they are having values 10 and 20. We are going to add both of them and then we are going to place the result in the variable A. And this is what we mean by an instruction, right? We say this is assembly language instruction. We will see that later. Not later, it is actually not part of operating systems, fine. Now we will be adding B and C and then we will be storing the result in A. This is what we mean by an instruction, and this instruction has some data, right? Data means values of variables, and we are having it in the code segment. Let us assume our code segment is actually, see, our code segment will not only have these two variables, it will also have some more variables which are used in our program, right? See, this is the code. This code will not only have this instruction, it will have a lot of instructions, and in all this instruction, lot of variables will be used. So our code segment is having lot of lines of code. Among them, one of the lines is this line, right? Also, our data segment will have lot of variables, out of which two variables are nothing but B and C. We will also have some more variables. Now let us assume our data segment is present in 2 pages, right? 2 pages. See, even this process will be chopped off as pages, right? Because anything which goes in RAM should go in terms of pages, because our RAM has been divided into frames. So anything which is going into the RAM should go in terms of pages, and so this process will also be divided into pages. Now let us assume the way we have divided the process is in 1 page, in 2 pages are actually allocated to data, right? Data. What do you mean by data? The values of variables, and let us assume the value of B has gone to this page, B equal to 10, and the value of C has gone to this page. See, this page will also have some more variables. I am not indicating here, right? Similarly, this page will also have some more variables. I am not indicating it here. So the value of B is present in 1 page, the value of C is present in 1 page. Let us assume this instruction, which means the code segment, is actually present in one more page. Right, in this page I have the code add of A, B, C, which means I am having the instruction. Also, this page will not only have this instruction, it will also have some more instructions, right? That is what we mean by program. Program is nothing but collection of instructions. So we are going to have lot of lines of code. Among them, one of the lines is add A, B, C. Fine. So as of now, we have lot of pages in our process. Let us assume that the variable B is present in 1 page, variable C is present in 1 page, and add A, B, C is present in 1 page. Now let us come back to our story. What we were discussing, we were saying that, so now what we were discussing so far? We were saying what will happen in case if I assign only one frame for every process, which means P1 is given 1 frame, P2 is given 1 frame, and P3 is given 1 frame. Now let us assume this is the frame which is given to process P1. Forget about these things, okay? Forget about this. As of now, think that this is the only frame which is assigned to our process P1, which means our process P1 can utilize only one frame. It cannot use more than that. Now what will happen is, let us assume our CPU is requesting for this instruction, add ABC, right? Now in order to execute this instruction, we definitely need this instruction inside the RAM, right? In case if this instruction is not present in the RAM, what will happen? Our CPU cannot access that instruction. So ultimately our CPU will, see, our CPU will first fetch this instruction, right? Which means it will place it in the register and then it will execute it. Now while executing it, it will understand that we are having two variables B and C, and these variables should also be fetched into the registers, right? Which means it will search for these two variables values inside the RAM. Now since we have only one frame, let us assume add ABC is the frame in which the page in which add ABC is present is actually placed in the RAM. See, our process is having, let us more pages. Let us assume these three pages are part of our process. Okay. Now we have only one frame assigned to this process, and so let us assume we have placed this page containing this instruction inside the frame. Right. Now can we execute this instruction? Now what our CPU will do is, CPU will first ask for the instruction, fine, using the logical address. You know that logical address will be converted to physical address, and using the physical address it will actually fetch this instruction, fine. Now while executing this instruction, it needs the values of variables B and C, right? Variables B and C. Now what it will do is, it will request for values of B and C in the RAM, which means it will search inside the RAM. Now what will happen? This will result as a page fault, right? Which means after going to the page table entry, which means the present or absent bit, we will come to know that our page containing the values of B and C are not present inside the RAM, right? Because see, we have only one frame assigned to this process, and in that one frame we have placed this page, so there is no space for these two pages, and so these two pages are present inside the hard disk right now, right? Fine. So what we will do is, okay, this will result as a page fault. So what we'll do is, we will replace this instruction, which means we'll replace this instruction. Let us assume we have first come across the variable B, right? So what we will do is, we will replace this page over here, right? This is what we mean by page replacement, right? We have replaced this page with this page. Fine. Now after placing this page, it needs the variable C, right? It needs the variable C. See, one more important point. Whenever a page fault happens, the instruction will be executed again from the beginning, okay? Which means the CPU is actually executing this instruction, right? Now while executing this instruction, it cannot find the page containing the variable B, and so it has led to page fault. Now what it will do is, because of page fault, it will load this page over here, replacing this page, right? Now after loading, this instruction should happen from the beginning, which means the execution of this instruction will start again. What I really mean by this is, in case if page fault happens, the instruction will be executed again, starting from the beginning, right? Now what will happen? Again we will need this instruction, right? So what we will do is, we will as of now this page is present over here, right? Now what we will do is, since we need this instruction, we will replace this page with this page again, right? Now what will happen? Now again we will come across, now while executing this, we will start the instruction again from the beginning. Why? Because it has led to page fault. So what we will do is, we will place this instruction over here, and then we will again start the execution. Now once we start the execution, we will again come across a situation where the variable B is not present. So again we will load this page over here, replacing this page, right? So what will happen is, in this frame, we will first place this page, and then we will replace this page with this page, and then we will replace this page with this page, and then we will replace this page with this page, and this will keep on happening. Okay, this is what we mean by thrashing. See, what is actually happening here? Page faults are happening repeatedly, right? Why it is happening? Because we have not allocated the number of frames in the correct way, right? We have allocated. Why this problem happened? Because we allocated only one frame for process P1, right? But with one frame, we cannot execute this instruction. And so I can tell you that with one frame, we cannot execute this process or this program. So for process P1, one frame is not enough. We might have to allocate more number of frames, right? See, what we were discussing, I was saying you that in case if we allocate 7 frames for this process, because we have 7 pages, it will lead to not using virtual memory concept, right? In case if you are not using virtual memory concept, our degree of multi-programming will come down, and so our CPU efficiency will come down. So we cannot do that. Now can we assign only one frame thinking that it will increase the degree of multi-programming? Though assigning only one frame for this process, increases degree of multi-programming, it is introducing its own disadvantage. What is the disadvantage? It is actually leading to repeated page faults, right? See what is happening here. Page faults are happening, keep on happening, right? Initially we were having this page inside the RAM and we were not having this page, and so it led to a page fault. So we placed this page over here, and then we were again executing this instruction. When we are starting the instruction, we were not having this instruction, so again it led to page fault, right? So we were placing this page over here, again it led to a page fault because of this variable, and then we were placing it over here. So page fault is keep on happening, repeat. So ultimately we are not doing anything productive, right? We are simply keep on replacing the page, which means the number of the page faults are repeatedly happening, right? That is what we mean by thrashing. So thrashing means page faults are repeatedly happening, okay? Number of page faults are very high. Now what will happen if number of page faults are very high? It will actually decrease the efficiency of CPU, right? Why? Because our CPU will request for an instruction. So in order to execute that instruction, we might have to wait, our CPU might have to wait for a long time because the page has to be moved from hard disk to RAM. That is what we mean by page fault, right? And you know that accessing a hard disk is very time consuming. Hard disk is the slowest memory, right? See, in case if there is no page fault, we don't need to access the hard disk. We can directly read from the RAM, so it will take very less time. But in case if page fault happens, in order to get the byte, it will take a lot of time, and so our CPU might have to wait for a long time, right? So, but here number of page faults are very high, right? Page faults keep on happening. So ultimately our CPU efficiency is going to come down, right? So we cannot assign very less number of frames to our process. So we might have to assign the correct number of frames to our process, right? We cannot assign too many frames to our process. That will reduce the degree of degree of multi-programming, and it will decrease the CPU efficiency. We cannot assign too lesser number of frames. What will happen over there is number of page faults will keep on happen. Number of page faults will increase, and that will degrade the efficiency of CPU, right? So both cannot be done. So we might have to assign some number of frames in such a way that number of page faults are less, as well as the degree of multi-programming is high, right? So we might have to come up with some strategy through which we will be able to find out how many frames should be assigned to a particular process, right? See, we came across three concepts over here, right? Frame allocation, page replacement, and thrashing. Anyway, we are going to see examples for this, but I assume that you are confident with frame allocation. What is meant by frame allocation? Frame allocation is nothing but number of frames we are going to assign for a particular process, right? For example, let us assume these three pages are assigned to our process. Now in this case, our process P1 can use only these frames. It cannot use any other frames. Now in case let us assume page number 0 is present here, page number 1 is present here, and page number 5 is present here. And in case if our CPU is asking for some other byte, in page number 3 it is asking some byte, so we need page number 3 inside the RAM. So what we will do is we will replace one among these three pages with this page, right? That is what we mean by page replacement. Now among these three pages, which page should be replaced? That is being decided by our page replacement algorithms. We have first in first out page replacement algorithm, last in first out page replacement algorithm, least recently used page replacement algorithms, a lot of things. We will see that later, okay? That is a very important concept. We'll see that later. Fine. So that's what I want you to understand. What is meant by frame allocation? Now what is meant by thrashing? Thrashing is nothing but repeated number of page faults, which means page faults keep on happening, as a result of which we are not executing any instruction, but we simply keep on taking the data from the hard disk, right? That is what we have seen. We were actually keep on replacing this page with this page, this page with this page, this page with this page, right? Ultimately we are not executing anything. So because of this repeated number of page faults, we are actually coming across a situation called as thrashing, and thrashing will degrade the CPU efficiency too much, right? We should always avoid this thrashing concept, right? So in order to avoid thrashing, what we should do? We should try to reduce the number of page faults as lesser as possible, right? See, because of repeated number of page faults, we are getting thrashing. Now in case if we make sure that the number of page faults are as lesser as possible, thrashing will not happen, right? Fine.